So finally we come to the most important number system, base 2, which we call binary, which uses just two symbols, 0 and 1. As you probably know, binary is the numbering system which suits computers best because computers represent everything as bits, that is, an off state or an on state, and typically we think of this off state as being represented by 0 and the on state as being represented by 1. I'll say more about bits shortly, but for now let's just look at counting in binary. The striking and confusing thing about binary is how quickly it starts using digit places. For instance, down here, you only have to get to the equivalent of decimal 12 before you're already using 5 digit places. This is of course a consequence of the fact that binary only uses two symbols, so you're going to cycle through digits very quickly. But aside from using so few symbols and quickly filling up digit places, binary works just the same as the other positional notation systems. So you may be wondering, if binary suits computers naturally, so why do we bother with octal and hex at all? Well, because it takes so many digits to express even small quantities in binary, it makes them inconvenient when we have to write out numbers and such in binary. And this is actually where octal and hex are helpful, because they can serve as more compact ways of writing binary. The way this works out is that if you write the octal equivalent of a binary number, that octal equivalent, essentially what happens is that each octal digit represents 3 respective digits in the binary number. And similarly in hex, each hex digit represents a respective group of 4 binary digits in the binary number. So using octal and hex, you spare yourself the bother of writing about 3 to 4 times as much. So consider the binary equivalent of octal 722 is 111010010, and this B simply indicates this is a binary number, and these underscores are just for visual separation so that I can group the digits into groups of 3. So these two quantities are equivalent. Well, it turns out that the equivalent of octal 7 is 111 binary, and the equivalent of octal 2 is 010 binary. And if you notice up here, 7, this corresponds to this group, and then this corresponds to this group, and then this last digit corresponds to this group. So what you have is that each octal digit corresponds to the respective group of 3 digits in its binary equivalent. The payoff of this is that then, if you want to mentally convert between octal and binary, all you have to do is memorize the equivalent of octal 0 to 7 to its binary equivalents. So if you simply memorize this table here, you can very easily mentally convert any binary number to octal or any octal number to binary. So let me give an example. So we have octal 4713. In binary, that would be 1001110011011. And I simply did this by looking at 4 here. 4 is equal to 100B, and then octal 7 is equal to 111B, and octal 1 is equal to 001 binary, and octal 3 is equal to 011 binary. You may be wondering, well, what if the binary number has a number of digits that's not divisible by 3? Well, the answer simply is that you group it into groups of 3, and you add zeros where necessary. So what we have here is the equivalent of 027 octal. The same is going on with hex and binary, except one hex digit is equivalent to 4 binary digits, not 3. So these two quantities are equivalent, and in fact hex 3 is equivalent to 0011 binary, and hex A is equivalent to 1010 binary, and hex 5 is equivalent to 0101 binary. So to do any mental conversion between hex and binary, or binary to hex, you simply need to memorize this table, the binary equivalents of hex 1 to F. Understand that these special relationships between binary and hex and binary and octal arise from the fact that they are powers of their bases are powers of 2. They are base 2, base 8, and base 16. The mental conversion between binary and a number system that's not a power of 2, such as base 10 decimal, is not so easy because each digit of decimal does not correspond to a fixed number of binary digits, so things don't work out so neat. You may be wondering, well, do we use base 4 or base 32 or even base 64? And the answer is no, because they're not worth the bother, really. In the case of base 4, each digit of base 4 would represent 2 binary digits, and that's not a lot of savings to bother with. And in base 32, you would be getting, for each base 32 digit, you would get 5 binary digits. But the problem then is that you'd have to memorize 32 different equivalences between this base 32 number equals this binary number, and that would just make the mental conversion more difficult to deal with. And to begin with, it's kind of awkward to group the binary digits into groups of 5, so it's kind of an odd fit anyway. You should understand that octal, it's true that is an odd number of digits too, but octal really only is used in a few specialized places, and even then it's really going out. It's used, the only instance I really know of that it's used is in the case of colors, and also in the case of something to do with Unix permissions, which you may be familiar with. Aside from that, it's really not used much at all.